Hello, everyone. Today I'm going to talk about the space radiation detector and the class and the medical physics, the 563 dosimetry and radiation. Let me share my screen. So today I'm going to talk about the space radiation detectors. This actual talk is most likely covered from the citation from the one of the recent NASA project. And I want to talk about in this presentation is going to the overview about this space radiation detectors. So in general, introduction about the detector and what is the difference about the radiation detector requirement for this particular space, and what is challenging, technically challenging, which we have to overcome, and what is the actually current and recent trending of the detector for the space radiation detection. In general, the radiation detector requirement, as probably know, the large acceptance required, which we have to cover the large detection area because we want to catch the particle as much as we can. And as well as we need the high sensitivity volume of the detector, which requires detection efficiency in terms of the detected particle. So detection efficiency is really depending on what type of the particle, which is charged particle or neutral particle. Depending on the particle type, we actually think about how to actually improve the detection efficiencies we can apply. Of course, we need a good noise reduction, so nobody wants to have a huge noise on top of the signal. So that requires excellent the background discrimination that most likely can obtain by the combination of the beta counter or electronics, or sometimes you can utilize the software techniques. Then next one is most important, the parameters in the detector requirement, which is the energy momentum resolution and spatial resolution. This resolution is key part, and then determine that the detector's the characteristics. So energy momentum resolution and spatial resolution allow us to actually pin down to the next item, which is the particle identification. So based upon the energy dependence, momentum dependence, and then the resolution wise, and you can separate out the one particle to the other. However, there's a Heisenberg uncertainty principle. You can actually pin down to the smallest resolution because the energy and time is limited finite size, or space and momentum is also the finite size. So you can actually beat into this limit. This is a kind of example of the general particle detector requirement, which is very close by the community, which is the Jefferson Lab in the Newport News area in Virginia. So you can see that the first top picture showing that the whole A spectrometers, large angle spectrometers, and the bottom one is the whole C high momentum resolution spectrometer, which is kind of two different arms that's moving together and then catching the small that's the acceptance area and then detected particle. And there's a very different detector combination is laying on through the beam line and catching the particle and identify the particle. The other one is kind of large coverage of a detector particle detection coverage, which is the CDAP large acceptance detector spectrometers, which is showing that the left side picture. And as you clearly see that this kind of 4-pi the spherical type of the detector, you can see that the looks like the orange 6 segment and is composition about the drip chamber, the 3 layer of the drip chambers detector, and outside of it we have a time of flight, and there's a forward carriage detector combined with the electromagnetic calorimeter and the Cherenkov counter and time of flight. It's kind of the covering entire this the momentum space, and then and also the energy space, and they can covering the 4-pi area in the center mass systems, and then catching the detector as much as they can. And the GlueX detector, which they built recently about a couple of years ago, and they just focused on the generated the photon and then high energy photon and catching the glue experiment, and which is the gluonic component into the object, and explain about the GPT contributions, the gluon GPT contributions through the experiment. So far, there is so many people actually involved from the different country and different universities, because as you see that the huge detector requires a huge amount of the electronics, as well as a huge amount of the manpower. That's why the people are coming from the many different places, and of course you can recognize me among the people. However, the radiation detector requirement for the space quite different situation, because they are extremely different environment from one in the Earth. So for example, the extreme temperature, either super cold or super hot, and there's vacuum, so there's no shielding part, the structure at all. So it means that it must be compact, because you can put into the huge detector in the space, because you have to carry on by space shuttle. Space shuttle is finite, small aircraft, and you can't put into giant in this detector and put into the aircraft, right? So I mean that the compact, so you have a small mass and a small power consumer, because there is no power outlet outside the space, and also you have to take into account the radiation resistant electronics. There is no shielding outside, so your electronics may be dying as soon as going to the space. So also there's no orientation, so you can actually define the orientation XYZ in the Earth, but you can't actually define the XYZ in the space, and you have to define based upon your detector location. And then it should be the long lifetime, as I mentioned, that low power outlet there. So you have to running by the battery or the solar cell. So it's running by the long time, and you can travel the back and forth frequently to fix it or to improve the efficiency or detector, something like that. I want to bring up the radiation, space radiation environment. For example, that compared to the territorial and space, the radiation level about 2.25 microsievert per hour, but in going to the deep space in the galaxy space regions, we expected about 60 microsievert per hour, which is more than 200 times higher than on Earth. So it's the type of the radiation in the space. We take into account the three major radiation type, which is the solar particle events, the SCPE, so most like a proton or helium type of the ions, and around the energy about the moderated energy range. The second one is the galactic cosmic ray, GCR. It's also the moderated, the high energetic ion, but the ion species is going to be from the one which is hydrogen to the ion type of the nuclear. And the last one is the trapped radiation, which means the ions and electrons from the SPE and the GCR trapped, and that's going to be scattered by the planetary magnetic field. So it's by on Earth or on other the planet. So space radiation exposure is more pronounced beyond the protection of the Earth's atmosphere's magnetic field, which is the SPE or the GCR is introduced a very large variety of the radiation dose for the equipment or crew, or the radiation dose from the trapped radiation need to be accounted for the traversing the magnetic field. And this kind of variation of the GCR are not fully understood. So that's why we need to develop the different type of the detector, and then understanding about the distribution or understanding about the radiation dose. there is some issue for the space radiation environment, and I can read some things. So we have to understand the existing space radiation data set, and there's a gap between in terms of energy on the ion space, because we only see that the very limited radiation type on Earth, but going outside, there's so many different things we may never experienced about before. And secondly, we have to understand that the variation in steady state or storm condition. So it's kind of solar storms coming in or stable states, and there's so differences. There are so many variations play around. But there is no actually the limit. There is no actually the finite configuration. There's no actually the lab space experiment. It's going outside, and there's so many varieties play a role. And current radiation detector technology is very limited and very limited lifetime. Technology is limited, and lifetime is limited, the precision is limited, discrimination is limited, and directional sensitivity also limited. Mass, power, and volume requirements is so many subtles, but this is very critical. And then you have to understand these kind of this small or big items one by one. So limitation of the knowledge of the radiation environment is going to be impact. So about the space science and astronaut or earth science. So it's kind of boosting of our understanding or knowledge by developing the detector in the space. So talk about the technical challenging we have to overcome. So I'm going to talk about the CFIDS detector in particular, which is called the compact full field ion detector system. So this kind of a novel design and novel technology of a detector, most likely detector actually utilize technique of the Cherenkov detector, and they actually the 4-5 multi-dimensional detector systems, and also require the high radiation flux coverage, and for the longer time, which is they aim for the more than 10 years lifetime mission. And then in terms of energy, they can cover the more than 100 MeV of the electron, 100 MeV of the particle can catching through this detector. Precisions and for the radiation hardness and the thermal stability is going to be wider than before, and then that should be the pretty high resistance of the radiation environment, and in terms of also the temperature wise, and also they can beating with the low level of noise, and then as I mentioned, the multi-dimensional measurement using this kind of spherical shape and allows to catching the all directional particle going to, and it's also the some kind of compact size. So I'm going to talk about a little bit more detail about the structure-wise. So I mentioned the 4-pi detector, but there is some orientation, kind of different weight direction. So there's a couple of layers of the beetle detection and the rejection counter, a combination together, and they can actually determine the orientation of the particle going into, and that they try to remove the noise by the multi-layer of the detector combination, then actually reject it out the noise which they are not interested in. So that in order to do that, and then they can produce the interesting noise, interesting the signal, and then remove the background out of the signal. So there is a different type of the diode. They use the diode type, the detector, but there's a different type of the diode that they use, the zinc basis or the silicon basis or gallium basis. So it's a kind of small detector, but actually trying to picking up the better performance in terms of the relative output factor. So the couple of them actually the enhanced, but the other one is the lower, so it's kind of constant pro. So it's that they actually try to zinc oxide, oxide the diode basis to actually produce the better output compared to the silicon and the gallium cases. So but the other one case is kind of wavelengths. The sensitivity is quite different. So you have to choose that which one is better and which one is not better. So here's a lesson from the learn. The radiation detector issues is actually impacts the variety of the mission in both air and space. So understanding about the space, and then we have a better understanding of our measurement in the Earth. And deep space cases and the leveraging expertise in such a harsh environment, and silicon-based device in a harsh environment, the packings or micro-optics or space-based instrument should be the way advanced radiation detector technology, because maybe it's not going to working for the Earth-based detector. So it's completely new novel design and new novel technology required. But applications concept should be compact. And also the full field space radiation detector system should be carried out, because it's not really localized. It's kind of an entire space, and then it's kind of entire energy range. And energy spectrum is going to be not localized. It's kind of full range of the energy spectrum, or momentum range, and then the time structures. So the detector development proceedings and the WBG device for LET device or the Cherenkov detector device. So technology challenging must be identified and being currently addressed and one by one. So you can't carry out the answers, one device, but you have to do it again, and then you can pin down to your problem and identify a technology challenging. So this is all about for the overview about the space radiation detectors. I'm going to just showing about this one of the NASA project, which is the Picasso program, which I was involved a few years ago. Is the planetary instrument the concept for the advanced the solar system, the observation. So this required some kind of spectrum, which is the Lama spectrum or the Lip spectrum. See that the spectrum, and then the picking out which object target sample has some component of the organ structures, organ component in Mars or in Moon, so in other the planet. So it's kind of quite interesting, and then it was quite good progress in program. So thank you for your attention. If you have a question, let me know. Thank you.